I'm going to be discussing the condenser cleanliness factor and the types of instruments that are needed to make this calculation. The cleanliness factor is the ratio of the actual heat transfer coefficient to the expected heat transfer coefficient per the HEI published value. We will be focusing on these measurements and the recommended practices per ASME Performance Test Code for Steam Surface Condensers 12.2. Cleanliness factor is a bit of a misnomer. While the cleanliness factor of the condenser tubes does impact this value, the more common contributor to cleanliness factor degradation is air storage on the steam side. Any abnormal thermal resistance between the steam and the circulating water will degrade the condenser performance. Internal tube fouling and air storage are the two largest contributors to the additional thermal resistance. Ultimately, you want to operate your condenser at the lowest possible pressure based on the input conditions to extract the most amount of power. However, circulating water inlet temperature, flow rate, and condenser duty will cause the back pressure to change drastically, even if the condenser is operating at peak efficiency. The cleanliness factor is a very valuable parameter to monitor because it normalizes the performance factor for all ranges of input conditions. The bare minimum measurements needed to calculate cleanliness factor are the bulk average inlet and outlet circulating water temperature, condenser pressure, and circulating water flow rate. In addition, you'll need to know the number of tubes, tube OD, and tube length for calculating a condensing surface area, the tube material and tube gauge for the material correction factor, and the tube OD, tube gauge, and number of passes to calculate the circulating water velocity. Before we get into ASME's recommendations on monitoring accuracy, let's run through an error propagation exercise. I wanted to show some of the possible errors in the calculated cleanliness factor from the error in the individual measurements. This is a sample calculation from a medium-sized Westinghouse condenser. The given values here in the second column, treated as the true measurements, will give a cleanliness factor of 85%. Now, if we look at each input and give them an error, we can rerun the calcs on each individual error and see the effect on cleanliness factor. The errors I picked here are not extraneously large based on my experience, so this is fairly representative of the type of errors you'll see in cleanliness factor. So for inlet temperature, nominal value 75 with an error of plus or minus 0.5 degrees Fahrenheit results in a cleanliness factor error of approximately 1.5%. The outlet temperature of 94.5 degrees Fahrenheit with the same plus or minus half a degree Fahrenheit results in a cleanliness factor error of approximately plus or minus 4.5%. The condenser pressure with an error of plus or minus 0.1 inch of mercury absolute results in the cleanliness factor error of plus or minus 13% or so. And circulating water flow with an error of plus or minus 5% of reading results in a cleanliness factor error of approximately 2%. Now this last row is where I picked the worst error for each of the parameters shown bolded for errors that will drive the cleanliness factor calculation down, and regular text for driving the cleanliness factor calculation up. So based on these worst case scenarios of error in these four primary measurements, you can get a cleanliness factor anywhere between 70% and 108%. The point of this exercise is to reinforce how important it is to keep your measurements as accurate as possible. So now let's get into the finer details with each measurement. I will be referring to ASME PTC 12.2 for each of the essential parameters. The information outlined in the test codes is very valuable. It is the goal or target for each of these parameters. We may not be able to achieve the PTC 12.2 recommendations fully, but the goal is to get as close as possible. We're going to start off looking at the inlet temperature. This is the measurement with the least number of concerns. The performance test codes recommends a 4-wire RTD with an accuracy of 0.1 degrees Fahrenheit. But if the accuracy of another type of temperature sensor is proven, then it is fully acceptable to be used. The only concern with this measurement is instrument accuracy and calibration. The water is typically well mixed here, so there is no difference between multiple inlet temperature measurements. A bulk outlet temperature is more difficult to get a true bulk average as compared to the inlet. Instrument accuracy is the same at 0.1 degrees Fahrenheit, with the overall measurement accurate to 0.3 degrees Fahrenheit. The preferred location is far downstream to ensure good mixing, and it has been shown that Anything less than 1,000 diameters downstream, you do not see any additional error from heat loss or gain from the environment. But a big concern with the far downstream measurement is the possibility of additional water lines tied into the return line. That's when things start to get complicated, with additional temperature and flow rates required to compensate. There is a guideline in the test code for performing a stratification test. 5 points made on a single vertical traverse, and all 5 points must fall within a 0.2 degree Fahrenheit band. But I've come across very few condensers with an accessible downstream measurement point location that is suitable for a single point measurement. If a well-mixed downstream measurement location cannot be found, then an array of measurements should be installed at each outlet. And all of these guidelines and recommendations are just to get around the issue of thermal stratification. So how bad can thermal stratification be? Here are a few images from tube sheets that have had temperature sensors installed directly on the outlet of the tube. The number of instruments that produce these images range from several dozen to several hundred individual measurements. Bionetics installed these temperature sensors and generated all of the thermal maps based on real measured data using computer tools only to interpolate between measured data points. Images 1 and 2 are the same condenser. Image 1 has high air and leakage, and image 2 has low air and leakage. The difference between the dark red and the dark blue on this image is approximately 30 degrees Fahrenheit. And these two images are interesting because they show the different ways air is stored within the condenser tube bundle. And we refer to these two ways as either a stagnant zone or an air-bound zone. Image 1 on the left shows a stagnant zone, which is caused by high air leakage, or conversely, low pump capacity. In this situation, the air builds up, increasing condenser pressure and gas density until it reaches an equilibrium that is dictated by the vacuum pump capacity. The right side shows air binding, where a pocket of air sits in the condenser as steam flow pushes it toward an area away from the air removal zone. This type of air storage will exist at any level of air and leakage into this condenser. So the information obtained from the thermal maps is used in conjunction with computational fluid dynamics software to properly locate a suitable location for a single measurement point or an array of measurements. By modeling the outlet water box and piping, and using flow rate and these temperature profiles, you can visualize and quantify the temperature as it mixes and travels down the circulating water pipe. For this particular installation, the pipe went underground, right where you see it end here on the model. So there was no other downstream location accessible. So we were forced to find locations in here to install our temperature measurements. Here's the thermal distribution out of the CFD model on the previous slide. And this is where we can take and look at the number of instruments required, the position around the pipe, the depth that they need to be installed, with the goal to be as few instruments as possible and still give us a bulk average. Ultimately, we selected 4 temperature measurements for this installation, and here's the actual recorded data. Included on this plot in blue are the 4 outlet temperature measurements that we installed, with the black as their average, and the red value is the OEM temperature sensor that was installed at this plant. And there is a large discrepancy between the OEM temperature measurement and the 4 installed measurements of approximately 1.5 degrees Fahrenheit, which would translate into large errors in cleanliness factor. The next measurement we'll look at is the condenser pressure. And this is the one parameter with the largest impacts on the performance calculations. PTC 12.2 states an actual requirement of 0.05 inches of mercury. Several styles of taps are recommended with the caveat that they are designed and implemented properly. And these are basket tips, guide plates, and static taps. Also extremely important is that these measurements be made between 1 and 3 feet above the tube bundle. Turbine outlet measurements are unacceptable for condenser performance analysis. Absolute pressure transducers are the recommended style. Gauge pressure measurements introduce the additional potential error with the need to know the atmospheric pressure as well. The common issues that are found here is an unsuitable location that includes being too far from the tube bundle or near some sort of high energy input or drain into the condenser. The piping and tubing from the condenser to the transducer should run downhill to the condenser to allow for draining of the condensation that occurs on the inside of the lines. An EPRI study that was presented in 2014 went into great detail on the recommendations in the test code. All 3 styles that are mentioned were installed at several locations around the condenser. The results were favorable to all three designs if they were designed and installed as specified in the test code. And also from this study, there was no appreciable difference in pressure measurement at the different locations along the length of this condenser. From this, one pressure measurement per pressure zone is sufficient as long as the installation and design factors from the test code are satisfied. Circulating water flow rate. This is where the most complication is introduced, but it also has the largest upside. To calculate the circulating water flow rate, you need condenser duty. Most online values for duty are derived from a thermal balance that includes dozens of temperatures and pressures, each instrument adding error or uncertainty. The easier path in terms of the cleanliness factor calculation is to measure the circulating water flow rate. However, this is a difficult online measurement to make. The performance test codes recommend using velocity traverse, dye dilution, or ultrasonic time of travel tests, but there are not a lot of instruments out there for flow measurements and pipes ranging from 3 to 8 feet in diameter. So what we recommend, and we use ourselves, is to utilize the natural differential pressure producing features in the condenser circulating water system. The most common place for one of these pressure drops is at the outlet water box to circulating water pipe orifice. These pressure drops are repeatable and measurable. There are two important parts to making the measurement: selecting the best locations for the high and low pressure taps, and calibrating the instrument. The DP meter installed in the best location offers no value if you don't calibrate it to the total circulating water flow. And that's when the one-time traverse or dye tests are used to calibrate the DP meters. The next few slides will show how to select the best locations. We're going to go back to our CFD model, and what's really nice aspect to this software is that we can obtain both the temperature stratification data and the static pressure data from the same model. This model here is the same that I showed earlier for the outlet temperature. And in this installation, we found that we could get a low pressure location on the inside of this elbow and a high pressure location on the water box wall. And this provided the largest pressure drop, which is what you want for this measurement. The pressure difference between these 2 points at full flow is approximately 30 inches of water from the analysis. And you can see here at full flow, we were at 34, which is good agreement with the model. But it's also important to run the model at multiple flow rates, just so you know you have signal across all flow rates if you're running 1, 2, 3, 4 pumps. Here's another example. This particular condenser had 2 shells where the water paths cross each other on the backside. And I have a few planes shown here. The taps were installed on the water box walls, and you can see the majority of the pressure drop occurred from where the water box pipe to the outlet, or the water box to the outlet pipe at the first pass outlet here, with some other pressure drops occurring around the elbows. The estimated pressure drop from this analysis is 20 inches of water. And here it is compared to the total test flow that we did. And you can see our high flow rate was measured at 25 inches, so good agreement with the model. This last example is a more challenging situation. This particular unit had a ball cleaning system installed on the outlet of the condenser. So therefore we could not install our DP meters on the outlet side, which is the preferred location. So we ran the analysis on the inlet piping and found that there is a location with a suitable signal. And looking at the highlighted planes, you can see where they crisscross, and we can see a high pressure and a low pressure spot. Right here on the inside of that elbow and on the outside of that elbow. And looking at the other plane, you can see we get about a 25 inch of water pressure drop between those 2 points. The DP measurement was calibrated against a traverse test and showed a high-end pressure drop of 20 inches of water, which is also in good agreement with the CFD results. This method has a lot of benefits, but is not without its problems and challenges as well. First, you need to know if you'll have enough signal, and that's where the analytical tools are a good way to determine that. The installation locations also need to be located away from anything that can cause pressure disruptions, like ball screens or butterfly valves. If the valves ever run in the throttle position, then the pressure profile just up and downstream are going to be significantly impacted. And if there is a tap in that area, your calibration will not be valid when throttling. These DP meters typically come with remote seals that are filled with a fluid that's a different density than water. So if the taps are located at different heights, you need to compensate for that. And the taps can be subject to fouling or plugging and may need to be cleaned. So now let's go through a case study that shows how this instrumentation was used to identify the cause for performance degradation. This is a Westinghouse single pass, single shell design with divided water boxes, supplying circulating water to two tube bundles from a mechanical draft cooling tower. We installed an inlet measurement on each inlet water box and 8 total outlet measurements, 4 on each outlet circulating water pipe, 2 condenser pressure measurements, and 2 differential pressure meters for use with flow rate on the west and the east side of this condenser. This unit was just coming out of an outage. The plant was still performing maintenance on one of the 2 circulating water pumps, so only one circulating water pump was initially available. So this graph is showing that startup for the days when they were just running with one pump. Cleanliness factor calculated here in red. You can see it starts out at 70% before it starts dropping off and getting as low as about 60. The total flow rate was also decreasing, which is this green line up here. Started off at about 95,000 GPM, and before the second pump came online, it was at 88,000 GPM. When the second pump was put into service, you see the total flow goes up to about 135,000, which was well below the expected 2-pump flow rate of 155,000 GPM. The other thing of note in the startup data is this divergence of the east path flow in light blue and the west path flow in dark blue. And this suggested macrofouling of the west path that was the root cause for the reduced flow rate and the condenser performance degradation. And then when you can see the second pump come on, you can see the difference in the east and west flow paths are extreme. So we informed the plant of what we saw and told them they need to inspect the west water box at their next available outage. The next time the unit was brought down, the water boxes were inspected for debris. And you can see a significant amount of debris was found lodged in the tubes and lying in the bottom of the west inlet water box. Here and here. The circulating water pipe on this unit comes in from the cooling towers, and the east path tees off the top of the line. Then the line continues another 30 to 40 feet and elbows up into the west water box. So that piping was also inspected and revealed additional debris had accumulated in the elbow that feeds the west water box. After the debris was removed, here in the post-cleaning part of this plot, the cleanliness factor returned back up to 70%. The flow rates in the 2 paths were now approximately equal, and the total flow rate was to the expected value of 155,000 GPM. Real-time data analysis aids in identifying causes of high back pressure, whether it's from air leakage, poor vacuum pump capacity, or steam jet air ejector capacity. And by measuring the flow between the condenser and the vacuum pump as well, you can monitor your air leakage and your ejector capacities, saving troubleshooting time. The real-time cleanliness factor can be calculated and displayed with the right equipment, and the DP meters have been proven to be a reliable method of measuring circulating water flow rate. Condenser monitoring is essential for reliable and efficient plant operation. With only the few sensors discussed here, you can quickly distinguish the root cause of any increased back pressure as the issue arises, and make effective decisions regarding maintenance and repair. Thank you for your time today, and if you have a problem with your condenser or your condenser instrumentation, feel free to give us a call.